Curve C has this equation, and we're asked to determine in terms of natural logarithms the exact x-coordinates of the stationary points of C. Well, let's differentiate. Sine hyperbolic simply differentiates to cos hyperbolic, so I really wouldn't bring out exponentials here, just use that result. If you're going to use exponentials, which I will talk about, then do it after we've done the differentiation. And here we've got the chain rule, so we'll get minus 4 cos 2x. That's going to equal 0 for stationary points. Okay, method 1, we're going to work in terms of hyperbolic functions throughout. It is the quicker and easier method. The only downside is you've got to be really careful at the end to not miss any solutions. I will get onto that. At the moment, we've got a cos x and a cos 2x, so we really need to bring in double angle formulae to get it's in terms of a quadratic in terms of cos. Now, there's a formula. Well, for non-hyperbolic, it's cos 2a is cos squared a, sorry, 2 cos squared a minus 1. Now remember Osborne's rule, you get the same identities for hyperbolic trig, except when there's a sine squared, you just change it to a minus sine hyperbolic squared. So we can get exactly the same identity here. It's really quick. I'm just going to very quickly derive it in case you're like, oh, where did that come from? Well, you're going to have to know or derive that cos 2a is cos squared a minus sine squared a. This is again non-hyperbolic. And if we use Osborne's rule, then cos 2a would become cos squared a plus sine squared a. And then for the one above, we always use sine squared plus cos squared as 1. So sine squared is going to be 1 minus cos squared, and sub in for it, we're going to get 2 cos squared minus 1. We'll do the same sort of thing here, but this time it's going to be that, let me write it out actually, cos squared a minus sine hyperbolic squared a is going to be 1. Because I've used Osborne's rule again, yeah, because it was a plus, now change it to a minus, and therefore sine hyperbolic squared a is going to be cos squared a minus 1. If we sub that in here, we will get 2 cos squared a minus 1. And so that is how you can derive it. But you're going to have to start with the double angle formula for trig. Okay, let's now sub this in. So 31 cos x minus 4 lots of 2 cos squared x minus 1 is equal to 0. That's going to give me minus 8 cos squared x plus 4 is equal to 0. And we've got ourselves a quadratic in cos squared. There should be an 8 there. Nice. This will factorize, but just put it in your calculator. It doesn't say we have to show detailed reasoning or anything like that. We're trying to, like this is a time pressured paper. There's only 7 questions in it, but I think it's quite tough to do it in an hour and a half, personally. There's a lot to do. So cos x ends up being 4 or minus 1 over 8 when you just put it in your calculator. Okay, so at this point, we can use the arc cos function. Now, the only thing is we need to modify it. And I'll tell you why. Because if you have, say, sine x equals a half, there's actually an infinite number of solutions. X would equal, if we're doing degrees, 30 degrees, 150 degrees. Keep adding on 360 or minusing 360, you get loads. But if you ever do arc sine of a half, there's only one answer when you're working in degrees, and that's 30, because this has to be a one-to-one function to be defined. So solving an equation where you can get many solutions is different from putting it into a function. And hence, when you look in the formula book and see the arc cos function, it's been defined to be a one-to-one function. But what we're actually trying to do is solve cos y equals x for this, and then y ends up equaling ln x plus or minus the root of x squared minus 1. I will show you where that comes from in a minute, but it's been, in the process of deriving it, it's been like removed to make it a one-to-one function. But to get our solution here, we can use the arc-cosh function to help us, but we must include that minus as well. So we are going to get x equals ln, put in 4 first of all, 4 plus root 4 squared minus 1, that ends up being root 15, or 4 minus root 15. And then cosh x is actually e to the x plus e to the minus x over 2. It's always positive. So in fact, we're going to reject that one. If you end up putting it in, you'll see you get ln of a negative and you would reject it. So those are our solutions. Loads of candidates missed the second one. Okay, I'm not surprised because like you're in the exam, maybe you haven't, it's just so easy. But if you practice these questions, you see them coming up quite a bit. Look out for it. And then you'll be okay. Just going to show you where that minus comes from, because you might be wondering. So let's derive the arc-cosh function, but in the process, we'll see, we'll see the minus and then why we actually remove it. Okay, so let's imagine that f of x equals cosh x, and I want to derive the inverse. So what I would do is let y equal cosh x and try and make x the subject. And of course, it's going to be inverse cosh x, but we want to get it in terms of exponentials and so on. So it's going to be e to the x plus e to the minus x over 2. If I times through by 2, I'll get 2y equals e to the x plus e to the minus x. And then I'm going to I'm going to times through by e to the x now. I'm going to create a quadratic in terms of e to the x. So that means 2y e to the x will equal e to the x squared plus 1. And therefore, e to the x squared minus 2y e to the x plus 1 is equal to 0. And I'm going to now try and solve this for x, because that's what we do when we try and find the inverse. We try and make x the subject. So I'm actually going to complete the square. You could use the quadratic formula, but completing the square is going to be quicker. E to the x minus y squared will get us e to the x squared. It will get us a minus e to the x y and another one. I just need to minus the y squared and then add 1. And that means e to the x minus y squared is going to equal y squared minus 1. And we can take the square root. E to the x minus y is going to equal plus or minus the square root of y squared minus 1. See, I've got these two answers. So e to the x is going to be y plus or minus the square root of y squared minus 1, and x is then ln of y plus or minus the square root of y squared minus 1. If I then want the inverse, which is cosh minus 1x, what we would do is we replace the y's by x's, and to make it a one-to-one function, we either need to have a plus or a minus. You can't have both, and so the principal value is to take the positive. So we get x plus square root of x squared minus 1. But back to what we were doing, we weren't finding the inverse as such. We were solving an equation which kind of involved finding the inverse, but recognizing that we need the minus as well. So I'm really hoping I've convinced you about that you won't, if you did make that mistake when you did this paper, you won't make it again because you'll be on the lookout for it. This will apply for inverse sine hyperbolic as well. Okay, time to do a second method to solve this equation. The bad news is it's much more complicated. The only good news is that you'll naturally get the two solutions coming out. You won't have to kind of think about it as much as we did for the last one. Although once you practiced it, you just know to put the plus or minus in. So here goes. I'm going to get it now in terms of exponentials and solve it. So 31 e to the x plus e to the minus x over 2 minus 4 times e to the 2x plus e to the minus 2x over 2 is equal to 0. And I can times through by 2 straight away. 31 e to the x plus 31 e to the minus x minus 4e to, I mean, looking at this, it's not actually that obvious what to do if you haven't done it before. We've got this like horrible equation, but it's actually a hidden quartic. We can times through by e to the 2x, and we'll get 31e to the 3x plus 31e to the x minus 4e to the 4x minus 4 equals 0. I've got rid of the negatives now, the negative parts of the exponentials. And then I can rewrite it as 4, because I want to make that bit positive, 4e to the x to the 4 minus 31e to the x to the 3 minus, there's no e to the x to the squared, this minus 31e to the x plus 4 is equal to 0. I'm going to let u equal e to the x, so then we can see our quartic. 4u to the 4 minus 31u to the 3 minus 31u plus 4 equals 0. Do not start using the factor theorem to try and solve this. It's like not a show that question or anything, like, or sorry, detailed reasoning question. Just use the function on your calculator, polynomial degree 4, type it in carefully. So this term is 0. And we get 4 plus root 15. We get 4 minus root 15. That's our u. Remember, there's 4 roots, but the other 2 are complex. So reject complex. And then that's e to the x. So x would be ln 4 plus root 15 or ln 4 minus root 15. Okay, I've gone into quite a lot of detail on this question, but I'm hoping it clarifies and gives you, two solution methods. I would opt for the first one. Just practice and it will come together. Well done.